We've moved our way from a microscopic view of current to think about a macroscopic view of current. Now let's make it even a little more concrete by thinking about real circuits. And the entire next chapter that we're going to study in the future will be entirely on circuits. So that's finally where we're to. So there's a few ways that we're going to be simplifying circuits. So first, we're usually going to talk about ideal wires. This isn't the case always, but frequently our wires are going to be ideal. And that means that we have a resistance of 0 if it's an ideal wire. And so then over each piece of wire, we have a change of potential of 0. Why? Because we have current is equal to our change in potential divided by R. So the only way we can have a current through a wire is if we have and no resistance is if our potential drop is also 0. So sorry, let me actually show you the equation for that. I've rearranged Ohm's law here. So for the ideal wire, our potential difference across any piece of that wire is 0 if our resistance is 0, even if current is flowing. So that's our ideal wire scenario. And we're not always going to use that, but we're frequently going to use that, and you want to include that in your simplifications when you're working with circuits if it's appropriate and you're using it. Next, we are going to simplify our resistors, which is an object with resistance, by saying that it has a fixed resistance. And that means it's independent of temperature. Again, that's a slight simplification, but we really don't want to have complicated things where we're worrying about temperature in here. So we're going to say that resistors follow Ohm's law. And again, that's really good. That's not much of a simplification to make. In the real world, the effect of temperature is very small. So we're going to approximate many materials as perfect resistors, meaning that they have a fixed resistance independent of temperature. Lastly, we're going to have an ideal insulator. And we're going to treat many materials as ideal insulators, and we've actually already been doing this, for instance, air. We're going to assume that it has an infinite resistance. So what that means is current is 0, but we can have any potential difference that we want. So what does this mean? Let's go back to Ohm's law. One way of thinking about this is that our current is 0, our resistance is infinity. 0 times infinity, well, I guess that can be any number you want. I don't know, that math might bother you. A different way of thinking about it is just rearranging and saying we can have any number we want on top, but we're dividing it by a number that is going to infinity. Therefore, we're going to get 0. So this way probably makes a little more sense to you. So in our ideal insulator, we never have a current flowing because the resistance is going to infinity, but we actually can have any potential difference we want across it. So an example of this is, for instance, before when we had our parallel plate capacitor and we had wires connected to it, and we actually had an air gap. So we can actually have a potential difference across that air gap, right? Notice that here, there's no wire. So that's basically air right there. And we can put a delta V there, which is from one side to the other, because it has effectively infinite resistance. No current is going through it. So that's an ideal insulator, which again, we're going to use in many cases, which allows us to isolate things. What this simplified circuit model then looks like is that we're going to frequently have wires in our circuit, but we're going to treat the resistance of the wire as 0. So we're going to say it's an ideal wire, but we're really only going to do that if we also have a resistor, right? So here we have a resistor, we have a wire, and we have a battery. So in this case, we're going to say that, oh, I'm going to treat the wire as ideal, so it has 0 resistance, which means we have no voltage difference across it. So initially, the voltage we have measured with respect to the negative terminal of the battery, we have some delta V, which is equal to the battery. And we're going to say the potential difference in this case across the resistor is equal to the EMF from the battery, which is just delta V back. Now we don't have any change in potential along the wire because we're treating it as ideal. Once we get to the resistor, we have some linear decrease in potential because a current is flowing through the resistor. We then get to the bottom, and again we have no change in potential in this region of the wire because the wire is ideal. So again, remember that current is conserved everywhere. So the current we have coming out of the battery is the current we have flowing into the battery, is the current we have flowing through the resistor. So we get to apply Ohm's law to the resistor to actually figure out what that current is. And again, in this case, it's going to be the potential difference from the battery divided by the resistance of the resistor. So this is how we're typically going to simplify a circuit, by treating these wires as ideal, so saying that their resistance is 0. This is a really good approximation as long as the actual resistance of the wire is much, much smaller. So maybe this wire has 1 ohm of resistance, but if this resistor has 10,000 ohms of resistance, the wire really makes no difference. So that's why we can do this simplification. So let's do some quick conceptual practice thinking about Ohm's law and some circuits. So we have two different circuits here. We have identical batteries. We have this one circuit on the left with one battery and one wire. We have a circuit on the right with one battery and 2 wires. What we want to do is compare the current through these 4 labeled points. Now, the first thing you should think about is the fact that I only have wires. I don't have any resistors. What this means is we cannot use the ideal wire model. So we actually are going to define the resistance in each wire to be R. We can't set it equal to 0 because we have to have some sort of resistance in order to define our current, which is what we're trying to do. So one simple thing to note is that our current here at A must be equal to our current here at B due to conservation of current. So this is pretty easy. But now, how do C and D compare to each other, and how do those compare to A and B? Well, notice here that C and D are symmetric, that you expect the same amount of current to flow through each of these wires since they're on the same battery, right? And remember that this curly E is your EMF, that's your delta V battery. So there's no limitation to current that is flowing out. Instead, we know that the potential difference across these wires is the same. So if the potential difference is equal to the current through the wire times the resistance of the wire, we can then say that the current through C is equal to the current through D. Why? Because they have the same potential difference across them and the same resistance. So the only way that equation can still be true is if the currents are the same. So lastly, let's try to compare these two circuits and think about what is happening. This is where a future technique about combining resistances will actually make this a little more straightforward, but let's try to do it conceptually. So let's say that the first part of the wires don't matter, right? Let's just ignore that. That doesn't make a difference. Hopefully you see why. And we're also going to ignore that over here. So what we're then left with are 3 sections of wire. We have this section from there to there. We have this section here to here. We have this section here to there. So basically we have 3 comparisons. We have this current, we have that current, we have that current. Note that in each case, we're dealing with the same wire. And in each case, we are still dealing with our battery potential. Why? Again, if we ignore that first part and we set this to 0, right, the negative terminal of our battery can be 0, this top part is then just equal to VBAT. The top part here is equal to VBAT. The top part here is equal to VBAT. So we have the same potential difference in each case, the same resistance. So what we actually get to say now is that IC is equal to IA, which was also equal to IB, which is also equal to ID. The one thing that you should note is that we are not saying that the current out of the battery is the same. We were asking, what are the current through these 4 points? What is the current out of the battery? Well, remember the junction rule, that in this case, the current out of the battery is equal to IC plus ID, because it gets here and then splits. Here, my current out of the battery is just equal to the current through A, because that same current goes through B. So in fact, in the second circuit, the current out of the battery is twice as much as the current out of the battery here. But the current through the points, A, B, and C, D, are all equal. So please make sure that you have a conceptual understanding of current before you just start doing calculations. And again, in a future week, we're going to be thinking about circuits and start doing this more in a quantitative way. But right now we're focused more at the fundamental conceptual level.